So we're at 3.12 in the textbook, and there it defines the null space of T. So here we are assuming that T is a linear map from V to W, okay? So here, null of T is all the vectors in V such that T of V gives you 0. Now the immediate consequence is that null T is a subspace of V. And how do you prove that? Well, proof, we'll go by the 3 steps rather than just 1 step. So first of all, A, what's T of 0? We prove that
0.
Yeah, this is equal to 0, right? So if T is a linear map, this is always true. But that means 0 is in the null space of T. Because by definition, anything that produces 0 after applying T is in the null space. So 0 is always in the null space. Okay. B, if U, V are 2 vectors in the null space, what does that mean? That means T of U is
0.
0. T of V is
0.
0. And what do I want to prove? I want to prove that U plus V is in null T. To prove that, what do we do? T of U plus V, we have to compute this and we have to show that this is 0, right? So what is that? That's TU plus TV, which is 0 plus 0 because of the given. And 0 plus 0 is 0. And that shows that U plus V is in the null space. Then part C, if C is in the base field, right, and U is in the vector space, null of T, then T of U is 0. So, i.e., U being in null T, that means TU is 0, that's what it means. Then T of CU, by homogeneity of the linear map, this is true, but that's C times 0, which is 0. So we have CU in null T. So we proved the 3 conditions for being a subspace. So 3.14 is proved. Can somebody explain to me what injective means? What's injective?
Is that if an element in the set A all equals in the element in the
So if you have a function from A to B, what about it?
and all elements in A
Uh-huh.
is paired with all elements in the B by 1 by 1.
Well, it's also known as 1-to-1.
1 to 1, yes.
Yeah, 1-to-1. But what does 1-to-1 mean?
So that every element in the A
Uh-huh.
is a pair like 1 to 1 to the
No. So there, it's a bit different than 1-to-1 correspondence. There's 1-to-1, and there's 1-to-1 correspondence. 1-to-1 correspondence is what you're trying to explain. Every element in A is paired with every element in B. uniquely, and that means the size of A has to be the same as size of B. That's one-to-one, one-to-one correspondence. But what one-to-one or injective means that every element in A is paired uniquely to some subset of B. So not everything in B is targeted, so you just have some subset of B, so that everything in A is paired with that. So it's something like this. An example of this is what, say, 1, 2, 3. And then here, let's say 11, 15, 17, 19, something like that, okay? And then if you have that one, so that it misses 17, or you have 1, 2, 3 elements, 1, 2, 3 elements, and they have the exact pairing, right? One unique. That's injective. There's one-to-one. Now, a better way to state this property is the following. If f of x is same as f of y, then x and y should be the same. That's injectivity. Well, you know, this is the simpler version to prove, but really what it's saying is that if x and y are different, it never goes to the same thing. So this is equivalent to saying that if x and y are different, then f of x and f of y are different. This is the true statement for injectivity, meaning that you can't have two different things going to the same thing. You get that? That's injectivity. But if you have P implies Q, then this is also what do you say? If P implies Q, saying P implies Q is the same thing as not Q implies not P. Does anyone remember what this means? Or there's a name for this. What's the name for this? If you have P implies Q as the original statement, and this is called the contrapositive of the original, right? So this is really the definition in the true spirit of what injectivity means. But often in practice, when you try to prove something, this is easier to work with. Because this is like something not happening. It's harder to say, it's hard to work with not equal. It's easier to work with equal because we're more used to equal signs. But you can see that this is negated, this is negated, and we switched it. So these are contrapositive of each other. Right? So that's our definition of injectivity. So are we all good? You remember what injectivity means? Okay, it's also known as one-to-one. Okay, there's a theorem in 3.16 that says if, let's say T is a linear map between V to W, okay, is injective if and only if null of T equals to 0. Okay. Sorry, I've been writing capital N, but I just realized that probably the textbook has lowercase n. So forgive me for switching from capital null, capital N to lowercase null. All right, so proof. We have to show this, right? With that assumption. Okay. So let's try to show this way. So here, T is injective. Okay. So suppose T is injective. Okay. Then, since T of 0 is 0, any linear map has that one, right? Any V in V such that of v is 0, this is another way of saying that v is in the null space of T, must satisfy v equal to 0. Right? Because that's what it says, right? T of v is same as T of 0. They're both 0. Therefore, v must equal to 0. I'm just using this definition, right? But look at what we did. We took an arbitrary element from null T and found that no matter how much we try, we end up always picking 0. What does that mean? Null T must be? Just 0. So that shows that null T is 0. Now let's prove the other way. Suppose null T is 0. Okay. Then we have to show that T is injective. If T of x or T of u is equal to T of v for some uv in v, okay, then T of u minus v, well, that's T of u plus negative 1v, which is, by additivity, this is T of u plus T of negative 1v. But now you have the homogeneity, which can bring the negative 1 outside. So that's same as T of u plus negative 1 T of v. But wait, that's same as T of u minus T of v, right? But didn't we say T of u and T of v are the same? Right, that's our condition. So this must be 0, right? Okay. Therefore, what do we know about u minus v? If you apply t and you got 0, that vector must be in the null space. That's the definition of the null space, right? Null space is collection of all such vectors. Anything that you apply t and you get 0, that means it's in the null space. So we found that this is in the null space, but that's 0. That's our assumption, right? It's a trivial space. So the only way that this is in the null space is when u minus v is 0. But if u minus v is 0, then u is equal to v. But now let's talk about range. What's the range? I think this is also lowercase. Range of t. Well, these are vectors in the target space where TV is equal to W for some V in V. And again, we're assuming here T is a linear map from V to W, okay? Okay, under this definition, again, we can show that range of T is a subspace of W. Okay, proof. A. How do we know that 0 is in range of T? How do we know that 0 is in the range of T?
T of 0 is equal to 0?
Yeah. right? So this 0 is in V, this 0 is in W, okay? Yeah. So for example, if this was from R3 to R2, this is really 0, 0, 0 on the left one, this is 0, 0. So even if I'm using the same 0, don't think of those two zeros as exactly the same, they're different. One is in V and the other is in W. But definitely, because T of 0 is 0, 0 is always in the range of T. Okay, B. Suppose U, W are in W, no, range of T. Okay. Now what does that mean? U is equal to T of some vector in V, right? And W is also another vector in V. Okay, then U plus W is T of V1 plus T of V2, which is T of V1 plus V2. That's the additivity of a linear map, right? So since V1 plus V2 is in V, this thing here is in V, we see that U plus W is indeed in the range of T. So C times, C is in F, and let's say W is in range of T, so that W is equal to T of V for some V, okay? Then C times W is equal to C times TV, which is equal to T times CV. And since V is a vector space, any scalar times V is in V as well, right? So that shows CW is again in range of T. Okay. All right. 3.20, surjective. Okay, now who can tell me what surjective means? What is surjective? Anyone? Do you remember what surjective? Yeah?
It's like the A-B thing you showed earlier,
Yeah.
but instead of B having more, it's A having more.
It's about right. Okay, so if you have function from A to B, you said intuitively you have more A than B. It's not exactly, but you could have either same number of elements or slightly more, or many more.
Mm-hmm.
But well, that's not always what's needed. 1, 2, 3, 4, and then let's say A and then B. You could have everything going to A. Is that surjective?
No, it's
No.
one form.
No. You need at least one to go to B, right? So that's surjective. That's also surjective, meaning that any element in B is targeted. Okay? That's what surjectivity means. Is that good? Right. So nowadays a lot of people use the word onto. So if you say a function is onto, that means the range is exactly all of the target set. Okay? In our context, what it means is that T in L V to W is surjective if range of T is same as the entire W. Okay? That's a way to say everything in W is targeted. Okay? So there's this 3.22, which is fundamental theorem of linear maps. And the formula is that if T is a linear map from V to W, then dimension of V is same as the dimension of the null space of T plus dimension of the range of T. Do you remember seeing this in the previous linear algebra course? Something similar? No? Who remembers such a thing? You kind of see it? Okay, yeah. Yeah, you're shown this formula, but I doubt that you did much proofs there. So this is very handy to prove a lot of non-trivial corollaries. But before we prove this theorem, look at what kind of work we've already done for this formula to make sense. See, we're talking about the dimension of the null T. We can't talk about dimension of null T unless we know that null T itself is a vector space. Only vector space we can talk about its dimension, right? So dimension of the null T is a possible thing because we know that null T is a subspace of V. And dimension of the range T is also possible because we know that range of T is the subspace of W. Okay, so that's something that we're trying to prove. Okay? All right, so how do we prove this? So, proof. Since null T is a vector space, take a basis V1 through Vm of null T. Now, this is a linearly independent list, and because null T is a subspace of V, that's what we proved before. We say that V1 through Vm is a linearly independent list in V. Okay, so since this is linearly independent in V, we can extend this to a basis that will show V1 through Vm and U1 through UK of V. Okay, so if you have this much setting, now tell me the dimension of the null T. What's the dimension of null T?
M.
Okay, it's M. What's the dimension of V?
M plus K.
M plus K. Okay. And then, therefore, if this equation is to hold, this has to be dimension K. If we show that this has dimension K, we're done. Okay? All right. So, how do we do that? Well, so claim T of U1 T of UK is a basis for W, the range of T. Okay. If we show that, then we are done, because that shows that range T is dimension K, and of course M plus K is M plus K, and we're done. Okay, so we just have to show this and we're done, right? Okay, to show it's a basis, we have to show that it spans, right? So let's first, we have to show that it spans and it's linearly independent. So let's do one by one. Okay, A, span. So any W in range of T satisfies T V equals to W for some V in V, okay? But because this is a basis for V, any V that you chose can now be written as A1, V1, all the way through AM, VK plus B1, sorry, this should be M, B1, U1 plus da da da, BK, UK. Right? Now, T of V is equal to T of A1, V1, AM, VN, which is T of A1, V1, AM, VM, plus T of B1, U1, BK, UK, by additivity. If you think of this as this plus that, then being linear, you can split them out, right? But then this is in the null space of T, isn't that right? See, V1 through Vm is a basis of null T, so anything that's spanned by V1 through Vm is in the null space of T. If you take any element in null space of T and apply T, what do you get? Zero. That's what it is, right? So this is going to be 0. And then this one, by using linearity, you can split this as B1 T of U1, da da da, BK T of UK. Oh, so this is indeed in the span of T of U1, T of UK, right? Okay. And because this is W, I should have said W equals. So we've managed to say any W is in the span of this. So that part is done. B, linear independence. Suppose C1T of U1 plus da da da, CK T of UK is equal to 0. And then we have to show that C1 through CK is 0, right? But then you have, by linearity, this is same as T of C1 U1 CK UK equal to 0. Now, because this, when T is applied, you get 0, what does this tell us about C1 U1 CK UK? this must be in
Null space.
the null space of T, right? But we know that null space is spanned by V1 through Vm. So it's A1 times V1 plus da 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 A M Vm. Now move everything to the left side, and now you have negative A1 V1 plus da 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 plus negative AM Vm plus C1 U1 plus da 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 CK UK equal to 0. Okay, now what? What do you know about these vectors? V1 through Vm and then U1 through UK. They form a basis for V, which means these vectors are linearly independent. Therefore, we know that. So by linear independence, we know that negative A1 is 0, negative da da da, negative AM is 0, C1 is 0, all the way up till CK is 0. Okay, so we proved what was to be proved, which is C1 through CK has to be 0, and that's done, right? And that's the conclusion of the proof of the claim. And because we finished proving the claim, the whole theorem is proved. So now we can erase this and say QED. Okay, so that was a very important theorem. That's why it's called the fundamental theorem of linear algebra. Let me write down some consequences. Corollary 2.23, no, 3.23. Okay. Suppose T is a linear map from V to W, and the dimension of W is less than, strictly less than dimension of V. Then T cannot be injective. Okay. As I said, this is a corollary. So let's first write down the formula that we have, which is that dimension of V is equal to dimension of null of T plus dimension of range of T. That's the fundamental theorem of linear maps. And because range of T is a subspace of W, we know that this is less or equal to dimension of null T plus dimension of W. And that's strictly less than dimension I'm just quoting this. I'm replacing dimension W by dimension V, and because this is strictly more than this, I end up with a strict inequality. Okay, can you finish this proof? Yeah, what do you do?
If it's injective, then the dimension of the null T should be 0, right?
Yeah,
So then dimension of V is strictly less than dimension of V, which is
Right.
contradiction.
yeah. So, but if T is injective, we know that means that null of t is 0, so that the dimension of null of t is a 0. And we get above, and above says dimension of v is less than 0 plus dimension of v, but that's impossible, right? Yeah, which is a contradiction. Now, this proof looks somewhat puzzling, but think of it this way. If you have a map from a bigger space to smaller space, and you still have to satisfy this is bigger than this. So that means this has to be a positive dimension, right? So think of it this. If this is 5 and this is 4, then this must be what? 1. It's forced to have some positive dimension, right? But if it's positive dimension, then the null space is not the trivial space, so it can't be injective. So that's the intuitive idea, but this will be like a very rigorous proof that builds on the previous theorem, right? Corollary again. 3.25, 3.24. Suppose T is a linear map from V to W, and dimension of V is strictly less than dimension of W. Then T cannot be surjective. Okay? Well, let's try that. So we start from dimension of V equals, so proof. We start with the fundamental theorem, which is dimension of V is dimension of null T plus dimension of range of T. Okay. Again, we want to show by contradiction. So suppose T is surjective. Now, what do we know about surjective maps? If T is surjective, the range is equal to the entire space, right? Right. And then we have dimension V equals the dimension of null of T plus dimension of W. Okay, but we know that dimension of W is bigger than dimension of V. So this time we can replace dimension of W by dimension of V. And now we'll subtract dimension of V both sides. What do we get? If I subtract dimension V, these are numbers, so I can definitely subtract. If I subtract dimension V both sides, then we get 0 less than 0 is bigger than dimension of the null of T. Is that possible? No. Vector spaces can only have non-negative dimension, right? So this is a contradiction. Okay? Hence, T cannot be surjective. And once again, I mean, you can kind of see why it has to be, because if W is a bigger space, so if you have a map from R2 to R3, you're trying to make the map T take all of R3, right? So, and it's saying that's impossible. Now, however, there's something that's clearly mind-boggling that you learned in the previous set theory class. What's the cardinality of R3? It's same as the cardinality of R, which is known as C, the continuum, right? C is the cardinality of the continuum. So if you just look at R3 and R2 just as purely sets, then you can make a bijective map between them. Okay? What we're just showing is that that bijective map cannot be made so that it's a linear map. So you even like R2 and R. If you have R2, which is a plane, and you have R, which is a line, they have the same cardinality, meaning that you can construct a map which sends every point on R to exactly one point in R2, and this is a one-to-one correspondence. So everything is targeted. Such a map does exist. You can construct them, but what we just showed is that that map cannot be a linear map. Now, what's even harder to prove, that you can later learn how to prove if you learn something called topology, is that such a map cannot be made to be continuous. So such a map has to be highly discontinuous. So one of the things that topology wants to know is that if you have a one-to-one correspondence, you have the same size set, is there a way to make this map to somehow preserve the connectedness of the space? And the answer is no. So that's a topic of topology. Okay, so maybe with so many sub-indices, you might be a little afraid to think about what it means, but all I'm saying is think about a system, something that looks like this. You have, say, 3x1 plus 2x2 minus x3 equals to 0, and then x2 plus x1 minus 4x2 plus 5x3 equal to 0. That's like this, right? If you view this as this, what's the value for n? N is 3. So this is the case when n is 3. What's the value for m? 2, right? M is 2. Okay. Which one is the number of unknowns? N. Which one is the number of equations? M. Is it okay? All right. So in this system, n is the number of unknowns and m is the number of equations. And being homogeneous means that the right side is 0. Okay? Right. Now, such a system always has a solution. What's the solution?
Everything is 0.
Everything's 0. x1 through xn, you just set it to 0. Okay? But sometimes the question is, are there non-trivial solutions? Okay? If you have some set of equations like this, can you have solutions that are non-trivial? So for example, can you have 1, 0, -1, 2, something like that? So you could have some zeros somewhere, but you want at least one non-zero value in one of the unknowns. Okay? And to answer that, you can really rephrase this as let T be a map from Rn to Rm, or Cn to Cm, okay? Where x1 xn is mapped to a11 x1 an1 xn a1m x1 anm xn, right? Definitely this results in how many components? M components. So that's m real numbers. See, this is a single number. You compute this, you get a single number that way, right? So you get 1, 2, 3, 4, all the way to m. So definitely this gives you a map from Rn to Rm. Okay. So here's how you apply 2.23. So 3.23, or maybe 3.23. Okay. So while we were showing that, so here's our theorem. If m is less than n, then there exists non-trivial solutions. Which is something that we've always known. We are told this fact, even if we didn't know how to prove it. If it was like, if you have n number of unknowns, so if you have 3 unknowns and just 2 equations, then there are infinitely many solutions. Not just the zeros, but there are more. You've heard of that, right? Yeah. Just same deal here, right? Now, how do you prove it? Well, proof. Apply fundamental theorem of linear maps. Okay. FTLM. And that says, we apply that for this t. Okay? That says null of t has a positive dimension. Okay? If m is less than n, m is the dimension of w and n is the dimension of v, right? Because it's v is Rn and w is Rn. Right? So you use the same deal as we did 3.23. You see that this has to have a positive dimension. But being positive dimension means, if it was 0 dimension, that means 0 is the only solution, right? But if it's positive dimension, that means there's more solution than just 0. That's how you apply the fundamental theorem of linear maps, okay? Okay, and we can also do it for 3.26. Well, so in this case, since when you have a non-homogeneous in that case, on the right side, you have C1, C2, Cn. Okay, so these are the constants. Okay. Again, you work with the same linear map. Okay, and this time, here's the theorem. If this time m is greater than n, in other words, if you have more equations than the variables, right? In that case, what did we learn in 3.24? That such a map T cannot be surjective, right? So here's the consequence. If m is greater than n, then the system will not have a solution for some C1, Cn. Okay, there's a choice of C1 through Cm so that the solution doesn't exist. Okay, and what's the proof? We just apply 2.24, which says that if the target space has bigger dimension than the domain space, then it cannot be surjective. So apply 2.24 so that T is not surjective. Okay. Now what that means is that in such a case, there exists, this means exists, C1 through Cm that's in Rm, right? So that T of x1 through xn is not equals to C1 through Cm for any vector in your domain. Okay. So Rn is the domain. Anything in here looks like this. So I'm really saying TV equal to W cannot happen for certain W's. W's they all look like this, right? So not being surjective means that there's a choice of C1 through Cn so that it doesn't have a solution. Okay. Yeah. Okay, so and these are something that you've heard about before, even in algebra class. Yeah, you're told that if you have too many equations, then just if you have 3 variables and 4 equations, it might turn out that you don't have any solution at all especially if these equations are incompatible. I mean, sometimes you might have three unknowns and 4 equations, but that 4th equation is just a linear combination of the other 3, so it's not a new equation. In that case, you might still have a solution. But you can always make these, if you're free to choose this non-homogeneous part, the constants, then you can make these so that there is no linear relationship between them, so these are all different. And you have more equations than the variables that you have to satisfy the equation for, then there's no way to make every one of these hold, right? So that's something that you've known since your algebra days, but to prove it rigorously, you needed this fundamental theorem of linear maps. Okay, so that's what we learned.